Today on Macaulay Math, we're looking at Riemann sums and the definite integral. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 23 on Riemann sums and the definite integral. Our goals for today. We're going to understand the definition of Riemann sum. We're going to evaluate a definite integral using a limit process and also geometric formulas. Finally, we're going to evaluate the definite integral using properties of definite integrals. In the last lesson, the concept of the integral as the area under a curve which can be approximated using rectangles was explored. In this lesson, a limit process will be used to allow the number of rectangles to grow to infinity as the width of the rectangles falls to zero. So first, a Riemann sum, and the Riemann sum is going to look very similar to what we've been doing for the last couple of lessons because it talks about the area under the curve as the sum of a number of rectangles under the curve. And when we look at a curve and we talk about a given interval from A to B, I'm not going to draw in all of the rectangles because we're going to eventually let them go to infinity. But what we're essentially trying to figure out is some value delta xi here, some width, with some value f of ci, where this value here is going to be my ci. And what we're going to end up doing is we're drawing a bunch of these rectangles in and having a bunch of different delta i's. And what we're going to eventually let them do is we're going to let these go to zero and let the number of these rectangles increase to infinity. And again, that's very difficult to draw, it's very difficult to visualize, but it gives you a general idea of what we're doing. Now, if you look at the definition of this definite integral, if f is defined in the closed interval from a to b and the limit of the Riemann sums over the partitions delta. So what we're doing is we're letting those partitions fall to zero. And then this here represents the height and this here represents the width. And each of these different CIs calculates different heights, and each of these calculates different widths. But what we want to do is we want to let the widths fall to zero and the number of those rectangles increase to infinity. And so when that happens, we can replace that with this notation of the definite integral. Remember that this value a is we're going to call the lower limit of integration, and this value b here we're going to label the upper limit of integration. How do I use this process here to prove a definite integral? Well, let's go ahead and try that. So if you recall from that last page, here is a definite integral, and we are going to start by using that definition, which is the limit as the change in delta goes to zero of the sum as I goes from 1 to n of f of ci times delta xi. What do we need to do first? First thing we're going to do is we're going to say, okay, let's talk about delta xi because that is going to be our partitions. Now, I want to make it easy, and so I'm going to say that I'm going to let all of my partitions be of equal width. And what that's going to help me do is I'm going to make it a single delta x. Now, I know that I have an upper and lower bound, and so I want to figure out how I'm going to divide these into my subintervals. Now, if I knew it was like 10 subintervals, I'd go 4 minus negative 2, that's 6, and then I divide by 10, and then each of these deltas would be 6 over 10, 3 over 5 wide. So we're going to do that in general. So in general, it's going to be, this delta x is going to be the b minus a over the number of intervals that we're going to do. And so in this case, it's going to be 4 minus negative 2 all over n, which is going to be 6 over n. So at some point here, I'm going to replace this delta xi with 6 over n. And that's going to be good because that's going to simplify it into single terms of n that we can take a limit of, which is what we did in a previous lesson. Now, let's talk about this ci. How do I get those values? All right, well, this ci, we're starting at negative 2, and we're going to be adding these partitions to it over and over again. All right, so if I want to come up with this ci, in this case, it's going to be a, where we start, plus the counter that we're on, where we're at in the summation, times our change, delta x. In this particular instance, since a is negative 2, we can put a negative 2 there. And then since our partition width is 6 over n, we're going to go plus 6i over n. So our limit, as our partitions go to 0, of the sum of the heights by the widths is going to be the limit now as n goes to infinity. Now why does it change here? Because we want delta to go to 0, but we are replacing our delta x with 6 over n. So if we want delta x to go to 0, then we need to let n go to infinity, because when n goes to infinity, 6 over n goes to 0. As I goes from 1 to n of f of ci times delta x. Here we will substitute ci into the function. And our function is a half x, so we'll have the limit as n goes to infinity of the sum as I equals 1 to n of a half x, right? That's what our original function is, half x. But our x's are calculated using this ci expression. So negative 2 plus 6i all over n times delta x, which is 6 over n. This resembles something that we've already done. If you recall, in the context of the sum, n is a constant. All right, so let's make this a little bit easier on myself, or at least try. In this case, I'm going to move some constants out. So I have 6 over n, that's a constant, and a half is a constant. All right, so let's move half times 6 is going to be 3. So let's move that 3 over n out. And now I want to separate the sum into 2 summations. And so what I'll do is I'll write it like this. I'll say it's the limit as n goes to infinity of 3n, and then it's the sum as I equals 1 to n of negative 2 plus, and 6 over n will be a constant, so I'll put that out in front, and then write the sum with I left alone. And so now I'm going to use, from the last lesson, use summation formulas. And so we recall the limit as n goes to infinity, we've got the 3 over n. And then when you change this sum into summation notation, if it's just a constant, it's just going to be the constant times n. So this becomes negative 2 times n plus 6 over n. And then if you recall, the sum as I goes from 1 to n of just I was n times n plus 1 all over 2. So we're going to do that substitution as well. And so here I've got n times n plus 1 all over 2, parenthesis to make it look correct there. And so now I'm going to do some simplifying. We're going to simplify and distribute the 3 over n to each term. All right, so before I can do anything here, let's talk about what I'm actually going to do. When I multiply 3 over n times negative 2n, the n's will cancel, and I'll get the limit as n goes to infinity. This first term here is just going to end up being negative 6, and then plus. Okay, let's see here. If I distribute here, when I go to do this multiplication, this n and this n will cancel out. 3 times 6 will be 18. Again, these two n's cancel out, so all that's left on the top is n plus 1. And then on the bottom, I've got n times 2, so I will have a 2n there. And I can calculate each of these limits fairly easy. The limit of a constant is just a constant. And then here I'll have 18n over 2n. And since the degrees are the same, the limit is just a ratio of the leading coefficients. 18 over 2 ends up being 9. So this thing ends up being 3. So my definite integral of this expression ends up being 3. Now, we can look at that. Here is my function, half x, from negative 2 to 4, and we can see that it's just a linear equation. And if we want to talk about the area between the curve and the x-axis, we have these two areas right here. Now, since they are triangles, the areas can be added fairly easy. If we look, I have 2 long and 1 high, so 2 times 1 is 2 times a half would be 1. I have a width here of 4 and a height here of 2. 4 times 2 is 8, times a half is 4. 1 and 4 should be 5, but we just calculated that to be 3. Now here's the issue. When the curve is below the x-axis, the definite integral will count this as negative area. So the area between the x-axis and the curve is actually going to be 5 units, but the definite integral will be, this will have a value of positive 4, and this part will have a value of negative 1, giving us the 3 that we got right there. Some properties of definite integrals. If you have a definite integral that's defined at a, from a to a, the definite integral will be 0. If you have a definite integral from a to b, it will be the negative of the integral from b to a. If you have a constant times a function, you can bring the constant out front. And then if you have the sum or difference of two separate functions, then it will be the sum or difference of the integrals. Note, continuity implies integrability. So if it is a continuous function, you can integrate it. Additionally, if you want to find the integral of a given region, it can be broken up into the sum of the parts. So if the integral from A to B is here, can be broken up into the sum of the integral from A to C, and then add that to the integral from C to B. A couple of examples. Write a definite integral that represents the area of this region. Okay, so our region is defined by this function 6 minus 3x, and it goes from 0 to 2. So here's going to be our lower limit of integration. Here is going to be our upper limit of integration, and we are going between the equation here and the x-axis. So our integral will be written as the integral from 0 to 2 of the function that we were given, 6 minus 3x dx. That one's a little bit easier than the last one. Here we have a function that is not defined by x's, but is defined by y's. So when we think about our rectangles in this particular instance, we're drawing them this way because our function is defined by y. So in this particular instance, here is our upper bound, here is our lower bound, just like it was along the x-axis in the last problem. So we can define this integral as going from 0 to 2 of our function f of y minus 2 quantity squared, and then our variable of integration will be y. Example, draw a picture for the area under a curve represented by the definite integral, then use a geometric formula to find the area. Okay, so if it's just a constant, and remember a constant the graph of a constant is a horizontal line. All right, so if I go to draw this, my lower bound and upper bound goes from 2 to 4 on the x-axis, and then up here I'll have 25, and so here is my function, and then the area in between will just be this area right here. And then it wants me to use a geometric formula to find the area. That's fairly easy. It's just going to be length times the height. In this case, it'll be 2 times 25. So it's going to be 50. All right. Next, draw a picture for the area under the curve represented by the definite integral. Then use a geometric formula to find the area. Again, here I have a linear equation. So if I go to draw that on my x and my y axis, I'll start at 0, I'll go to 4, and 0 in this function here is going to give me 0. 4 in this function is going to give me 1. So I will have a line that goes like this. My area under the curve looks like this. And then to find that area, we'll use the geometric formula, a half base times height. In this case, a half times my base of 4 times my height of 1, which will just be 2. Next, draw a picture for the area under the curve represented by the definite integral. Then use geometric formula to find the area. So here I have a definite integral that's defined by negative a to positive a and some value a here. And so in general, we're going to consider a to be a constant. All right, and I can do that fairly easy. We will call this here our x-axis, this here our y-axis. We'll go from negative a to positive a, so that magnitude should be about the same. And then we'll have an a here. So the absolute value function, if you recall the absolute value y equals absolute value x, that function there is just that v function. And so if I make it negative, it's going to flip it across the x-axis. And at x equals 0, I'll have 0 plus a, so I'll have a here. And then if it becomes a minus the absolute value of a becomes 0. So I'll have a line that goes to here. Negative a, the absolute value of negative a is positive a minus a is also 0. So I'll have a line that goes like that. And then the area of that region would be this area right here. And so there's my diagram. And then if I want to calculate my area, again, I'll use a half base times height. In this case, this length here is a, this length there is a, so my base is 2a, and then my height is also a, and so a half times 2 is 1, a times a is a squared, so that is going to be the area of this definite integral, regardless of the value that you choose for a. If you square that value, that will be the area of this region. All right, final example. Use the diagram to evaluate the following definite integrals. Okay, so this right here is my f of x, and it is defined by 1, 2, 3 line segments. And so if I want to find the definite integral from 0 to 4, I want to find this area right here. And that'll be fairly easy because it looks to me like it is a square, a 2 by 2 square. So I'll get length times width, in this case 2 by 2, that'll give me 4. So there's my definite integral for that one. From 2 to 3, well, 3 is going to be approximately right here, and we will draw that in. And so that integral will be defined by this green area right here. And that thing is a trapezoid. And so the area of a trapezoid is 1/2 the height times the base 1 plus the base 2. All right, so let's calculate it for this one. In this particular instance, this is my base and that is my base. And so my height is technically the width of this thing. So I'll have 1/2 times, that width is 1. And then base 1 is this height right here, which I can see is 2. And then this height here, I can see, I'm going to guesstimate, is 3. And so I have 1/2 times 1 is 1/2. 1/2 times 5 is 5/2. Now finally, it wants us to find the definite integral from 2 to 6. Now from 2 to 6 is this distance here. So the reason I put this in is because I want to, before we leave, have a demonstration of this additive interval property. And what the additive interval property says, if you break it up into 2 parts, you can add the sums of those particular areas. So here I have this trapezoid, but over here I have a triangle. So what I'm going to do is I'm going to break it up into two separate integrals. I'm going to say that it is the integral from 2 to 3 of f of x dx plus the integral from 3 to 6 of f of x dx. Now I've already calculated this one from part B, and we know that it is 5 over 2. Now this one can be calculated with a triangle formula. Half base times height. The base goes from 3 to 6, so it'll be 3. And then this goes, the height will go from 3 all the way up to 3. And so it will also be 3. So I have 5 halves plus 9 halves is 14 halves, which is 7. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. How much money has the Star Wars brand generated since it came out in 1975? All right, this is going to encompass movies, toys, books, TVs, VHS. I know you don't know what VHS is. DVDs, video on demand, and other merchandise sales. As of 2017, it is $30.2 billion. That is a lot of money. That's all I got for today, folks. Have a good day.